Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcome Professor Manuel Minas da Piedade. Professor Manuel da Piedade completed his Bachelor of Science and PhD at the University of Lisboa. He is currently a full professor in the Chemistry and Biochemistry Department of the University of Lisboa. His research studies the correlation between the energetic structure and reactivity of molecules using calorimetric techniques, vapor pressure measurements, and computational chemistry methods. Dr. Manuel da Piedade has specific interests in the systematics of bond dissociation, entropies, crystallization, intermolecular potentials, and polymorphism in solids, computational chemistry, and biomaterials. So once again, welcome Professor Manuel da Piedade. Thank you so much for accepting our invitation. It is a pleasure to have you here with us. Please feel free to start your presentation.
First of all, thank you very much for the invitation. This is a good opportunity to share with you some of the things that we are doing in the latest years. And in my group at the moment, we have two main projects. One has to do with what I'm going to talk today, and the other one has to do with using calorimetry and some biochemical ancillary measurements to look at cell metabolism. Now, I'm at this center here, Centro de Química Estrutural, which is based in Lisbon and has two sites. The one that you see in the picture is the FCUL site, and there is another one at IST, which is an engineering school, and actually my former school, because I was at IST for many years before moving to the Faculty of Science. At that time, the Faculty of Science and IST were in two different universities that have merged, and so it's now the University of Lisbon. And this center is part of an even bigger structure called Institute of Molecular Sciences, IMS, which involves not only our center in Lisbon, but also a center in Coimbra and another one in Porto. Okay? So today, what I prepared was a fairly light seminar on this topic. We want to prepare or make a functional materials starting from an organic molecule and going to a crystal. And so the functional material is mainly based on organic crystals. Okay? And as an outline, I will talk about polymorphism, which I will define in a moment, but it's a very common phenomenon in organic crystals. Then I will talk about thermodynamics and the importance of thermodynamics to control and characterize polymorphism. Most of my examples will be about small molecule pharmaceuticals, and if you want a fairly good justification, this is the projected market for small APIs, active pharmaceutical ingredients, which are basically molecules which have about 20 to 100 atoms. And if you look at this bar here for 2024, this is about 200 billion US dollars, which is close to the, I would say it's 40 to 60%, if I didn't mess up the calculations, of the GDP of countries like Denmark or Portugal. Okay, so this is a fairly big market. And finally, I would like to talk a little bit about how important it is to have accurate thermodynamic data and pay attention to polymorphism to help people who are engaged, so theoreticians who are engaged in crystal structure prediction, which is a very important tool to help companies which are developing materials, in most cases pharmaceuticals, to predict how many polymorphs are expected if you start from a given molecule. And this example that I will give you is about this Best CSP initiative, which is a European initiative under the cost action. It's a cost action project, actually. And what we are trying to do is to get together theoreticians, thermodynamicists, crystallographers, people who study crystallization, for example, to come up with benchmark data that can help these people engaged in crystal structure prediction to not only improve and validate the methods that they are developing, but also extend them to property prediction. So, like, what is the melting point of a pharmaceutical? Okay? And so that's the outline. Now, what is polymorphism to start with? It's the ability of a substance to crystallize with different arrangements of the molecules in the lattice. And if you want an example, this is paracetamol, a molecule which probably all of us have taken at a certain time. And if you start with paracetamol, you can end up with this structure when you make a crystal, or you may end up with this structure. Okay, so the molecule is the same, but the crystal structure is different. Now, why is this important? Take, for example, this, which is normally called Form 1, okay? And it's normally the market phase of paracetamol. It's monoclinic. The density is about 1.4 grams per cubic centimeter. The melting point is 169 Celsius, and the solubility is 180 milligrams per gram, in this case, in water. And Form 2 is orthorhombic. The density is smaller, 1.33 The melting point is significantly smaller, 157 Celsius, and the solubility is larger, 202 milligrams per gram of water. And this 5% difference in density, 12 K difference in temperature, and 12% difference in solubility can have a big impact if you are using paracetamol as a drug. You are developing a tablet of paracetamol. And for pharmaceuticals, solubility is particularly important because if the solubility increases frequently, there is a very good correlation with bioavailability, which is very, very important if you are going to use it as a drug. Okay? Now, if you consider the process of going from a molecule to a crystal and then to a functional material, in this case, a tablet, okay? Polymorphism can strike here or even here, because if you crystallize the molecule either from solution or from a solid, you may end up with this form, but sometimes simply by changing the solvent, or if there are some impurities in your media, you can end up with a different crystal structure. And even here, even if you have this solid form, okay, and you are processing it using, say, micronization, a vacuum to dry it or whatever, you can sometimes end up with a different crystal form, okay? I had a student once who took some time to produce one specific polymorph of an organic compound, and he put it under vacuum, and not very high vacuum, just a rough pump, okay? And he ended up with a different crystal form. So he lost 3 weeks of work or something like that. So it's a phenomenon that you really need to control, okay? And if you think that this is only important for pharmaceuticals, it's not, because different polymorphs can have different colors in some cases. This is Roy. Roy is a very famous example of a molecule with polymorphism because it's, as far as I know, it holds the world record in the number of different crystal forms that have been isolated. And those crystal forms can change not only in morphology, but also in color. So you can have red prisms, yellow prisms, orange needles, and there are more. Okay? Now, why this happens? This happens because when Roy crystallizes, depending on the method of crystallization, the conformation of the molecule can change, and so the conjugation of this system, this pi system, okay, will change, and that will change the homoluminal gap, and so the wavelength of absorption will change. Okay, and this is, for example, the red prisms, which absorb at 451 nanometers, and the yellow prisms, which absorb at 415 nanometers. Now, for another example, take lasers. In the neodymium laser, for example, the emission originally is in the infrared at 1064 nanometers. But you can make the neodymium YAG laser emit green light at 532 nanometers. Now, to do that, you shine the infrared light on a crystal, and then green light comes off. But this crystal has to be non-centrosymmetric. Okay. Now, this is that we've studied for hydroxyacetophenone, and there are two crystal forms, one that we call form 2 and another one that we call form 1. And form 2 is orthorhombic, and there's this kind of wave packing. The form 1 is monoclinic, and there's this parallel sheet packing. Okay. Now, this form is non-centrosymmetric. This form is centrosymmetric, and so this is SHG active and SHG inactive. What this means is that this form can generate second harmonics, which is what you need to make that halving of the wavelength here, or doubling the frequency of the emitting light. Okay, so this is what these crystals do. Okay, and you can use this effect. This is SHG active, and this one is SHG inactive, to study the kinetics of phase transition, from form 1 to form 2. This is what we have done in collaboration with Gérard Coquerel in Rouen. Okay, and you can see here different kinetic curves that we obtained by looking at the phase transition at different temperatures. This is the degree of conversion as a function of time. And from these plots, you can take rate constants, and you can take energy of activation. Okay. So polymorphism can be a mess, because if you don't control it, you can have problems with the production of safe use of functional materials, medicines, and other functional materials. But it's often forgotten that if you don't pay attention to polymorphism, this is also a problem when you're trying to obtain thermodynamic properties, because different polymorphs, as I told you, are different materials, and so the entropies of formation will be different, the entropies of sublimation will be different. Sometimes the difference is negligible, but frequently it's not. If you look at Jim Chico's compilation on entropies of sublimation, it's not a curated database, but you can have a look and see that there are very, very large discrepancies in many cases. And probably some of these discrepancies are due to the fact that the measurements were made without the persons characterizing the crystal form that they were using. Okay? So polymorphism can be a curse if you don't pay attention to it, but it's also an opportunity, because if you control polymorphism, you can in principle tune the properties of a product without changing the molecule. Okay? Now, I will not have time to describe in detail how you go about polymorphism study, okay? And what I will list here is more or less the most important steps. And I could give a seminar about each of these steps, okay? So first you have to find the polymorphs, and usually you want to go straight from one to the other, but usually you go left, right, back, front, and then you end up finding a way to go selectively to a specific polymorph. So this is still very tricky. Then you need to characterize the polymorphs in terms of structures. So what are the crystal structures? What are the molecular structures within the crystal structure? So are there conformational changes? What are the differences in packing? Then comes thermodynamics, and you want to rank the stability of the polymorphs because you can have several polymorphs coexisting at the same temperature, but one of them will be more stable from thermodynamic point of view than all the others. And so all the others will try to transform into the stable one if the kinetic barriers are not large enough, okay? Now, you can then look at these two terms. Are the polymorphs related monotropically or enantropically? And what this means is if you have two polymorphs which are monotropic, one will be more stable than the other from 0 Kelvin to the melting point. If it's an enantiotropic relationship, there will be two stability domains. One will be stable up to a certain temperature or pressure, and the other one above that temperature of pressure. Okay, and so they will be related by a solid-solid phase transition. And you need to know where that solid-solid phase transition is, how fast it is. Can you reverse it very easily? Or once you go one way, you cannot go back because the activation barrier is too large. And what are the stability domains? If you want to know at which pressure and temperature you need to work to be sure that you are working in a stability domain of a specific polymorph. So that means phase diagrams, okay? And finally, kinetics, which is very not well-studied area. So that's, we know very little about the kinetics of phase transitions, and you would like to know rates, activation barriers, etc. Okay, so this is a lot of information that you need, and you can imagine that we need a huge amount of techniques to work out all these aspects of polymorphism. Okay. Now, what I will try to do now is to look at some case studies, right? Just to highlight important aspects of polymorphism. Okay, so polymorphism. These are 5 systems that we have studied. We have studied many more, but these are all active pharmaceutical ingredients. Okay, paracetamol is an antipyretic, analgesic molecule, which I showed you just a few minutes ago. Simvastatin is something that people take if they have high cholesterol and they want to control the levels of cholesterol. Now, dihydroepiandrosterone is used for obesity, lupus, and cancer. And these here are used to treat cancer. And these two systems, flubendazole and deralutinib hydrochloride, are very dear to me because they were done in collaboration with a good friend in the University of São Paulo, okay, Gabriel Araújo. Now, polymorphism is a very common property or effect in organic crystals, and it's very important for pharmaceuticals because 80% of all medications are commercialized as solids, and that's because it's easier to take a tablet than go to a center or whatever and get an injection or carry out bottles with liquids. So polymorphism, because it's so common in organic molecules, and so because most pharmaceuticals are organic molecules, is a major risk for the pharma companies, and they have to mitigate this risk, but they can also use it as an opportunity. Just to show you how important this is a timeline of some cases that happen where you had to withdraw a medicine, okay, because of polymorphism, a problem with polymorphism. The most famous case is this one, ritonavir, happened in 1998, and it really opened the eyes of pharmaceutical companies for how important it was to control polymorphism. Now, there are many other cases. The latest one that I found was in 2024, so not very far ago. Okay? So there was a contamination of a batch with one polymorph that should not be there. Okay? Now, what happened in the case of ritonavir was that when AIDS came up, the deaths were exponentially increasing, and then ritonavir came up. And so the deaths were going down, down, down. And then in 1998, there was a problem with ritonavir. The medicine was sold in those capsules, and in principle, there was inside a solution almost saturated or very close to saturation. And then they found out that the capsules had powder inside. So they were not able to produce capsules with clean solutions inside. Okay. And so they went up to try to find out what was happening. And this was really a very serious problem because ritonavir was the only medicine in the market which could be used to really control AIDS. Okay? So what they found was that they were marketing this form, okay, which was metastable relative to this form, but for some reason they had prepared it and were reproducibly prepared it in the production process. And then this one came out in the process. No one really knows how and why. And the problem was that this form 2 was 5 times less soluble in that solution that they had inside the capsules than the ones that they were using. And so it took them 1 year, I found out, to solve the problem. And there was, on one hand, the problem of a rupture of stocks, and then the medicine will not be available to cure people or at least to control AIDS. And on the other hand, the losses was an immense amount of money. Okay, so this is just for you to understand how important this problem is. Okay. Now, one example, Lotini hydrochloride that I studied with Gabrielle, it's a good example of the importance of crystal polymorphism now for patent litigation. Okay, so ritonavir was a problem of a medicine that came out from the market, and then you had no medicine to treat people. This one is about patent litigation. That's one of the aspects of this example. And the other one is how you can play with polymorphism as an opportunity for drug development. And this is something that we did in Lisbon. Here, Carlos, Hermínio, and Osvaldo were involved in thermodynamic part. Gabriel did a lot of work on solubility and preparation of the polymorphs. Rui Fausto helped us with infrared spectroscopy, and Pam and Stephen Byrne helped us also with infrared spectroscopy data that I'm not going to show. Okay, so the drug that I hope none of you will have, because it's used for lung cancer and pancreatic cancer, so 2 very serious forms of cancer. Okay? And what happened is that the drug marketed by Roche and came in 2004 under this name, Sifa. Okay, and then in 2000 it was introduced in India, and the Indian company Cipla starts developing hydrochloride polymorphically at one of Roche's price. So litigation started, and what Cipla claimed was that Roche patent did not specifically cover polymorph P, so they were allowed to sell this rulatinium hydrochloride because they were only selling pure polymorph P. So litigation took them years, and they reached settlement in 2017. If you go to the internet and try to look at one of these settlements, you cannot imagine the amount of money involved because the salaries of lawyers huge, and so this is really serious business. Okay, now what Gabriel found was that he determined the solubility curve or this of form B, which was the market form. Okay, but then he tried to study also form A, and what he found is that form A is much more soluble than form B. And usually, if you're trying to develop a drug, if you can work with a form which is more soluble, and you can guarantee that is sufficiently stable to be used, then it's much better because normally, as I said, there is a fairly good correlation between solubility and bioavailability. And if you have increased solubility, usually you can control better the bioavailability. And this is 3 times more soluble than this form here. You have to be careful because if form A is contaminated with form B, what happens is that you start the dissolution process through the form A profile, but then you quickly end up with form B profile, and so the solubility drops. So you have to pay attention to this. Now, usually you want to know the difference in stability between polymorphs, so the stability hierarchy. And thermodynamic is important for solubility, obviously, but also for establishing the stability hierarchy. And for that, usually you would like to know how different is the delta G of this transformation, okay? And if possible, you would like to know also the delta H and the delta S, because then you will know if the stability is entalpic or entropically controlled. Okay? So to do that, you can use solubility measurements to get the delta G. So if the metastable polymorph is stable enough during a solubility measurement, you can get the molar fraction solubility, and you can do that for polymorph P as well. And then you can get delta G of this phase transition. And if you then use a calorimeter, okay, you can measure the solubility, the enthalpy of a solution of one polymorph and of the other. You have to be careful because the amounts that you dissolve have to be exactly the same or as same as possible. Okay, and using this thermodynamic cycle, it's a very simple question that you can give to one of your students in an exam. You can get the enthalpy of the transition. And so, since we know the delta G from the solubility measurements and the enthalpy of the transition from the calorimetric measurements, you can also obtain the delta S. Okay, and in this particular case, you find that the stability of form B is larger than form A because it's endergonic, and also it's endothermic. So, and the enthalpic term is larger than the entropic term. This is enthalpically controlled. So, what is controlling the difference in stability of form B and form A is mainly the lattice enthalpy. Okay. So using calorimeters and solubility measurements, you can do this trick. Okay. Now, simvastatin is an example that I choose to show you that you can, in fact, evaluate if polymorphism is a problem or not. Okay. And we studied simvastatin. It was mainly the work of Abhinav, which is, he made a PhD in our group and is now in India. And then Carlos and Ricardo helped. Fatima is the crystallographer in our group, and Francisca Emerlin is a good friend that is in Bamberley. And Werner, they helped us a lot with the structural characterization. Okay. So in the case of simvastatin, if you want to know if there are polymorphs, one, and second, if polymorphism is a problem, you can, by the way, simvastatin is used for lipidemia, right? So if control high cholesterol levels. And when we studied simvastatin the first time, the first thing we did was a DSC, a thermogram, and from room temperature to melting point, and we see a clean melting without any signs of phase transitions that could indicate that there could be polymorphs other than this one that we were working with. And then we we went to lower temperatures, and we did find phase transitions. And this told us that there are, in fact, 3 polymorphs of simvastatin. And so the question is, if you try to develop a tablet with simvastatin, will polymorphism be a problem or not? Right? And in this case, not really, because these transformations are very fast. And we found that if you go up to room temperature or close to room temperature, so the temperatures at which typically you store a tablet, okay, these 2 polymorphs will quickly transform into form 1, which is the form that is stable at room temperature. Okay, and so this tells us that polymorphism, although it exists, it's not a problem, unless you want to store your tablets at -20 or something like that. Okay? But even if you transport it through a country where there are -20 in the winter and keep it outside, once you go inside your home where the temperature is close to 20, then the phase transition will occur and you will end up with formal again. Okay? So it's very important that you do these characterizations to understand all these aspects that I'm telling you. Okay, and as you see, thermodynamics is very, very important. Actually, we also studied simvastatin by heat capacity measurements, and so there are many techniques that we applied. We also use molecular dynamic simulations to try to understand what was happening. In the end, what happens and why the phase transitions are so fast and the conversion between polymorphs is so easy is because what's happening really is that the crystal structure of all polymorphs is very similar, except that molecule in this tail here has a different conformation. Okay, and if you study the crystal structures and the molecular conformation at different temperatures, we went from 167 K to 291. So we crossed form 1, form 2, or form 2, 3, form 2, form 1. You see that the only thing that is changing is this group here, which is rotating. Okay. Now, why is polymorphism important for this helping or very, very careful thermodynamic characterization of polymorphism important for people who are trying to develop crystal structure prediction methods? Okay, I've written here crystal structure and property prediction, but property prediction is something that is very, very, very incipient at present. Okay. So what they typically give us is what they call a polymorph landscape. So they use computer chemistry to calculate different crystal structures, and they will give you this landscape where each point represents a different polymorph, a different crystal structure. And as experimentalists, we know that they predict far many polymorphs than what actually we can find experimentally. And another thing that happens is that typically the differences in cohesive energy between the polymorphs are not the ones that we found experimentally. Sometimes they are very close, sometimes they are a little bit far. And so that's why that initiative that I told you about, that European initiative, which is called BEST CSP, okay? CSP stands for Crystal Structure Prediction, was organized. And so we have theoreticians, okay, and then we have people who are experts on solving crystal structures. We also have people who are experts on spectroscopic data, like infrared NMR, mainly infrared NMR. And we have thermodynamicists, so people determining heat capacities, entropies of sublimation, entropies of fusion, temperatures of fusion, solubility measurements. And what we do is the theoreticians will tell us, okay, there is these molecules which we find would be challenging and interesting for developing of our methods. And can you measure data that we need, crystal structures, fusion, whatever? And these are some examples of molecules that we are that we have in the pipeline at the moment, and there are others coming. And so this will tell you how important it is to pay attention to crystal structure before starting the measurements of the thermodynamic data in solids. Okay. So finally, message is to take home. Polymorphism is a very common phenomenon in organic solids. Each polymorph is a different material, really. So the molecule does not change, but it's a different material. If you control polymorphism, you can avoid manufactured problems, but you can tune the properties of a material in view of an application. Accurate thermodynamic data is critical for polymorphism control. Polymorphism should always be considered when measuring and reporting thermodynamic data on solids. And multi-component solid forms, it's something that I haven't told you about, but it's another way to turn the properties of a product in view of an application. Sometimes we can play a trick, which is put more than one molecule in the crystal structure. Okay? And finally, accurate thermodynamic data is critical for development of crystal structure prediction methods. So I have to thank FCT Portugal for funding our work. It's a very, very small pig at the moment. And this is the group as today. Hermínio, Carlos are senior members, and Ricardo, senior members, which were on thermodynamic, and Carlos is also a theoretician. He does molecular dynamic simulations, mainly developed force fields. Fatima is our crystallographer. Soli is an expert on interfaces and colloids. And these are the students at the moment. Inês is finishing the PhD. João is starting the MSc. These two are finishing the MScs. And Gonçalo is also finishing the MSc. And so thank you very much for having me.